How's it going, everyone? Welcome to this tutorial. Today we're going to be talking about the NumPy library, which is considered to be the fundamental package for scientific computing in Python. It's a super important library and the base for several other libraries like Pandas, which is primarily based on NumPy. We'll go through a brief background and then look at various functions that NumPy has and that can be used to delve deep into getting started with the world of AI. Okay, NumPy is a multi-dimensional array library that you can store all sorts of data in. You can store data in one-dimensional arrays, two-dimensional arrays, three-dimensional arrays, and so on. I use NumPy over Python lists. Well, the primary reason for this is speed. Lists are extremely slow to work with and NumPy is very fast. Say if you want to store a number in a list, say the number 5. On a list, it's going to have multiple attributes that the list will store for this single integer 5, which will be something like the size of the integer, the object type, the reference count, which is primarily how many times the integer has been referenced in the program. The object type is whether it's an int or a float or anything of that sort, and of course the actual number itself, which is 5 in binary. So it stores the number, the reference count, object type, size of the integer, and all of this for just a single number in lists, whereas for NumPy it's just the binary version of that integer. So because NumPy stores just a very small amount of memory as compared to lists, NumPy is extremely fast and efficient and is fundamentally used for scientific computing. Another reason is that NumPy holds its elements in contiguous memory locations. For an array, if you have 10 elements, the 10 elements will be stored in consecutive memory blocks on the computer, whereas for a list, they could be stored in any random memory location on the computer, not necessarily in contiguous memory blocks. And the last reason for this is that NumPy has no kind of type checking. So in a list, when you go through the list, you may have a bool inside the list. So in NumPy, there's no kind of type checking inside a NumPy array that happens, whereas in a list, as you go through the list, the elements may be of different data types, an integer or a floating point or a boolean value or so on, and there is type checking that happens every time you access an element. Whereas in NumPy, there is no kind of type checking for this. So that's another reason why NumPy is extremely fast. Okay, let's get started. We are over with the history lesson. And the first thing you need to do to import the library is import NumPy as NP. So NP is the two letters that you'll be using to reference NumPy after this has been imported. So once you have that imported, the primary thing you do with NumPy is arrays, and you initialize arrays using np.array followed by a parentheses, and then you put a list inside of that, say 1, 2 and 3 or 4, let's say. And if you want to print out a, let's see what happens, an array 1, 2 and 4. You can also have multiple dimensional arrays, as I said. np.array, and you can have 3-dimensional arrays, 1, 2, 3, 4, 2, 8, and then let's make 5, 6, 7, and another one with 9, 4, 20. Let's print out the value of b. This is the multidimensional array we got. It's a 3-dimensional array, and you can make arrays of any dimension you want. Suppose you want the number of dimensions of b. You say b.ndim and press enter, control and enter, and you get 3 dimensions. b.shape will print out the shape of the array, which is 2 by 2 by 3. a.d type, as in the name of the array followed by a dot d type will print out the data type of the elements in the array, which is an int 64. A dot item size gives you the size of each item in the array. A dot n bytes will give you the number of bytes that the array holds, 24 bytes. Suppose you want to access a particular element in the array. Say for this B array, I want to access the 8 element here. So you start from the outside and go in. So this is the this is a three-dimensional array. So you want an index 0 for the first part because this is the first block. Then you want an index 1 because this is the first one in the first block and this is the second one. Remember that indexing starts from 0, so this is 0 and this is 1. And then you want the third element of that first block, so it's 0, 1 and 2. So this is the B array, sorry. So B of 0, 1 and 2, this should give us 8, which it does. You can index any element you want using this notation. You can also do a group of elements with the colon operator. B of everything in the first dimension, 1 in the second dimension, and then let's say everything up to second in the third dimension. And this gives you an array. If you initialize an array of zeros, you can initialize an array of zeros using np.zeros and put in the dimension inside this. You can initialize an array of ones using putting an array inside the parentheses that follow after that. This is computing a little slowly today, I don't know why. 4 by 5 by 2 np.ones. You can also specify a data type after this. Int 16, which is a 16-bit integer. So if you want to store less amount of memory, you know that the numbers are going to be small numbers, then you can use a smaller memory data type to help you save memory and run faster. np.full can be used to initialize an array of any kind of dimensions with a specific number, not 1 or 0, whatever number you want. So a 2 by 4 array with all values equal to 89 can be initialized like this. np.full like can be used to initialize an array which is of the dimensions of the array that you specify here. So this has the dimensions of B. Remember the three-dimensional array we had B, and all the elements are valued at 4. Okay, let's go to random number generation, one of my favorite topics. np.random.rand, and you put in the dimensions inside of this 3.2.5 for example here, and you get an array with random values between 0 and 1 with dimensions what you specified here. Suppose you want to generate a random integer array, so np.random.randint gives you an array based on what you specify here, what you want the integer to be, followed by the size of that array, which could be, let's say, 3,6, and you get an integer. Okay, so this is the exclusive max value, not the value that will be filled in all of these. So numbers will range from 0 to 3 excluding 4. So this is the upper limit for the values that will be in this array. np.random sample p.shape. This can be used with a particular shape of an array to generate a random sample of that shape. Okay, let's talk about copying arrays. Let's say you have a equal to np.array 4, 5, and let's say it's np.ones, and now you want b equal to a, and then you put b of 1, 4 to be 0, and then let's print out a. Well, we expected a to be an array of all ones, but then we declared b to be equal to a, and we changed the value of array b. Why did the value of array a change at this position? The reason for this is when you initialize an array equal to another array, it basically passes the reference of this array to the new value that you initialize, and whatever changes you make to this will be affected in this. So if you want to declare make a copy of that variable and initialize it to another variable, you can use the a.copy function, the copy function for NumPy. And now if you make changes to array C, let's put it as 0 for this one, and the value of a doesn't change. We changed this one earlier when we did this, but when you make a copy of C and then change something in C, a doesn't change. Also, you can add, subtract, multiply and divide arrays easily. Suppose we have this array, you do a plus equal to 2, and all of the elements of the array a will get increased by 2. You can also do a times 5 and a minus equal to 4, let's say. You can also do stuff like np.cos, which is the cosine function, np.sine, which is the sine function, and so on, np.log, np.exponent, everything you want. Matrix multiplication can be done by np.mat_mul followed by the two matrices that you want to multiply, two NumPy arrays, but keep in mind that these dimensions should match, which is that the number of columns in A should be equal to the number of rows in B, otherwise this will show up an error. I won't initialize these arrays right now, but you can try them out yourself. Make array A equal to a 2 by 3 dimensional vector and B equal to 3 by 2, for example, and then multiply using this. You can do some last few quick functions that we'll go through. np.sum will calculate the sum of all elements in array A. np.max will give you the max of all elements in array A. You can also set the axis, which is the dimension that you want max along when you have multidimensional arrays. So A doesn't have an axis 1. Axis 0 is by default the horizontal axis, and 1 goes on to vertical, and when you have multiple dimensional arrays, you can increase axis and find out the maximum in any axis you want using this. You can also do np.min, so you can have an array which is named before with initialized zeros of 2 by 3 dimension, and then you make an array after with before, and you reshape that before to 6, 1. So the number of elements should match. This is 6 elements, this has 6 elements, that should match, and then you print that and you get this. You can also do something like a greater than 50, which will result in an array which has values, Boolean values, which say whether or not the value at that particular location in A is greater than this value or not. So that's about it for this tutorial. I hope you learned a lot. We went through a lot of functions, and make sure you try all of these out on your own. The link to this notebook will be in the description. Make sure to check that out. Thank you guys for watching, and I'll see you guys in the next tutorial. Bye bye.